to is on the addition rule and multiplication rule. The addition rule specifically deals with these compound events, and that's any event combining two or more simple events. And for example, those would be A or B or A and B. In this case, for the addition rule, we're going to be doing the A or B option. But this is for the addition rule, that's the probability that two events occur. Let's call them A and B. So if we have the two events A and B, we have the probability of A or B is equal to probability of A plus probability of B minus probability of A and B. Right? And we have two ways that we can have those events, A and B. First way is where we have the two events where they don't overlap at all. So because of that, that probability of A and B would then be 0 since they're just two separate identities. But the far more interesting method, and which is where this formula specifically comes from, is if we take the probability of A and add to it the probability of B. Notice how we have this middle portion right here shaded twice. And that is the probability of A and B, the intersection between these two events, where that's counted twice. And that's why we have to subtract the probability of A and B in order for it to only be counted once. So for example, let's say based on this table down here, if one subject is randomly selected from the 555 subjects given a drug test, we want to find the probability of selecting a subject who had a positive test result or uses drugs. So probability of positive test or uses drugs. So for the positive test, we have 45 in this cell and then 25 in this cell down here. And for the or uses drug tests, right, we have a 5 in this cell over here. Because of that particular formula that we just had, we would technically be adding another 45 and then subtracting it, since that's the intersection between the two. But we don't need to necessarily write all those steps. For that probability of positive test or uses drugs, we could just add these three numbers in the numerator to get 75. And then the denominator is just 555. So 75 divided by 555, we get a probability of 0.135. For disjoint events, A and B are disjoint or mutually exclusive. Those could be used interchangeably if they cannot occur at the same time or they have no overlap. Thus, both cannot occur at the same time. The addition rule then changes to probability of A or B is equal to probability of A plus probability of B. The probability of A and B then is essentially 0. And that is exactly what these two events A and B are that I drew here on the left. These would be an example of disjoint or mutually exclusive events. They don't share anything. The addition rule for complements is probability of A plus the probability of A complement is equal to 1. By algebra, we could rewrite this as probability of A complement is equal to 1 minus probability of A. We could also write probability of A is equal to 1 minus probability of A complement. So now for the next example, based on a journal article, the probability of randomly selecting someone who has sleepwalked is 0.292. And this is based on data from prevalence and comorbidity of nocturnal wandering in the United States general population by O'Hayan et al. From Neurology, Volume 78, Number 20. If a person is randomly selected, find the probability of getting someone that has not sleepwalked. Well, probability of not sleepwalk, that is 1 minus the probability of sleepwalking. And we were given that as 0.292. So 1 minus 0.292, that makes 0.708. Next we have this multiplication rule. And this is where probability of A and B is equal to the probability that event A occurs in one trial and event B occurs in a different trial. And it utilizes this special notation, probability of B occurring after it is assumed that event A has already occurred. So that's probability of A and B is equal to probability of A times the probability that event B is occurring after it is assumed that event A has already occurred. And when it comes to the multiplication rule, if we have the two events A and B as independent, if the occurrence of one does not affect the probability of the occurrence of the other. Events that are not independent are called dependent. And if A and B are independent, we can change our multiplication rule to be the probability of A and B is equal to probability of A times the probability of B. That probability of B occurring after A has already occurred, this is essentially the probability of B if they're independent. So let's say, for example, using 50 test results from the subjects who used drugs in example 1, which is written down here in this table, if 2 of those 50 subjects are randomly selected with replacement, we're going to find the probability that the first selected person had a positive test result and the second selected person had a negative test result. So probability of first positive and second negative. So from this table we could see the probability of being a positive test result is 45/50ths, and the probability of negative test result is 5/50ths. So to find this probability, we need to take the probability that the first is positive times the probability the second is negative, due to the fact that these were chosen with replacement. That then indicates that these are going to be independent. They're going to be independent because of that with replacement portion. So 45/50ths times 5/50ths, that gives us a probability of 0.09. Repeating part A now by assuming the two subjects are sorted without replacement. So now in this is going to be a dependent relationship. So we need to use that general form of the multiplication rule. Probability of first positive and second negative. First positive is the same, 45/50ths. But now for the second being negative, this will now be the second being negative after the first is positive. The numerator is still 5. We didn't touch the negatives. But now we change the total number of test results for this. Instead of being 50, we already used 1 here. So now we have 1 less, so 49 in the denominator. And when we multiply these out, we get a value of 0.0918, so slightly better probability of occurring than the first one. Sampling with replacement is referred to as independent events, and sampling without replacement is dependent events. We can further refer to small samples of large populations without replacement as independent when sampling without replacement and the sample size is no more than 5% of the size of the population. When that occurs, we could treat those selections as independent, despite the fact that they are technically dependent. As another example, let's assume that 3 adults are randomly selected without replacement from the 247,436,830 adults in the United States, and assume that 10% of adults in the United States use drugs. We will find the probability that 3 selected adults all use drugs. 3 is definitely well less than 5% of 247,436,830. We don't even need to do that calculation now. We already know that's the case. So from this, probability all 3 use drugs, the same thing as probability the first use drugs, and the second uses drugs, and the third. And since all those then are then independent because of the fact that 3 is less than 5% of the population size, we could just multiply all those. probability. So probability of the first times the second times the third. So 0.10 times 0.10 times 0.10. Or that 0.10 to the third power. That's 0.001. So 1 thousandths. When two different people are randomly selected from those in your class, find the indicated probability by assuming that birthdays occur on the days of the week with equal frequencies. We want the probability that two people born on the same day of the week. Because we're just referring to the same day of the week, we are not attempting to note these as anything that is independent per se. We know that the probability of the first born on a day in the week is 1/7. The probability that a second person's born on the same day in that same week is also going to be 1/7. So the probability that both are born on the same day is 1/7, due to the fact that we're referring to just any day there of the week. But for the probability that two people are both born on Monday, probability that the first is born on Monday is 1/7. Probability that the second's born on Monday is also 1/7. But now for both of them, we multiply the two probabilities to get 1/49. Now, modern aircraft are now highly reliable, and one design feature contributing to that reliability is the use of redundancy, whereby critical components are duplicated so that if one fails, the other will work. For example, the Airbus 310 twin-engine airliner has 3 independent hydraulic systems, so if any one system fails, full flight control is maintained with another functioning system. For this example, we will assume that for a typical flight, the probability of a hydraulic system failure is 2 thousandths. If the Airbus 310 were to have one hydraulic system, what is the probability that the aircraft's flight control would work for a flight? So probability of not failing. Well, we were told the probability of failure was 2 thousandths. So probability of not failing would take 1 minus the probability of failing. So 1 minus 2 thousandths is 0.998. So 998 thousandths. Given the Airbus 310 actually has 3 independent hydraulic systems, what is the probability that on a typical flight, control can't be maintained with a working hydraulic system? So this is the probability all 3 don't fail. So that's the same as 1 minus the probability of all 3 failing. So that's the same as 1 minus 0.002 to the third power. Toss that into a calculator, you get an answer of 0.999999992. Thank you.